In this video, we are going to continue on discussing how to solve linear ODE of order 1. Just to recall, so I recall a linear ODE of order 1 has the form ax y prime plus b of x y equals c of x, where a and b and c are functions of x only when a is not identically 0. So dividing by a of x will have the following form. We get the form of ODE of linear 1. First order ODE of linear 1 is y prime plus p of x y equal q of x. So this is the ODE we're going to discuss. Now in the case where q of x is identically equal to 0, then we get what we call the linear homogeneous ODE, and this you have already seen how to solve it. Now in the more general case, which is the case when q of x is not necessarily 0. So we want to solve this equation, the following equation star, when q of x is not identically 0. And you might have seen the previous video that if we have an equation of the form x y prime plus 2 of x, so let's remove this, plus 2 of x y equal to x. And we were thinking by what we should multiply the left-hand side in order to get, on the left-hand side, this is the left-hand side, in order to get a total derivative. And you can notice, just pulling the rabbit, that if I multiply by e to the x squared, I get the ODE e to the x squared y prime plus 2x e to the x squared y equal x e to the x squared. And now we can notice that the left-hand side is the total derivative. So this becomes e to the x squared y prime, because if you differentiate this product, you can use product rule, which is e to the x squared y prime plus the derivative of e to the x squared, which is 2x e to the x squared, and then times y. And this is equal x e to the x squared. And now we go back to the antiderivative method and integrate. We get e to the x squared y is equal e to the x squared over 2 plus constant, and then you get the solution y equal half plus c e to the minus x squared. So e to the x squared, the function e to the x squared, is called an integrating factor. And now the question is how to get the integrating factor in general. So in general, having an ODE, so consider the following ODE. Y prime plus p of x y equal q of x. And now I want to multiply, so the goal is I want to multiply, let's call this double star, by a function mu of x, so that the left-hand side of the equation, and this is my left-hand side, is a total derivative, which means a derivative of one function. So let's say, so multiply by mu of x. Let's see the equation that mu of x should satisfy. Then I get mu of x times y prime plus p of x mu of x times y equal q of x mu of x. Now notice that for the left-hand side, which is here, to be a total derivative, here I have mu of x times a derivative plus some function times y. So choosing mu of x such that the derivative of mu with respect to x equal p of x mu of x, then the left hand side becomes mu of x y prime plus mu prime of x y equal q of x mu of x. And now, in this case, this will be a total derivative. This will be the derivative of mu of x y prime. So just to notice, the integrating factor, mu, so this is called now integrating factor, is a function that I should multiply by the ODE double star so that I have the left-hand side a total derivative. And this tells me that mu should solve the following ODE. So if mu is the solution of this following ODE, so let's call it ODE 1, then mu is an integrating factor of the equation. So let's go to a new page now, and I said that if I have the ODE y prime plus p of x y equal q of x, then the integrating factor solves the equation mu prime of x equal p of x mu of x. But notice that this equation is linear homogeneous, because if I bring mu to the other side, this becomes mu prime minus p of x mu equal to 0. And you already know how to solve this equation. We solve the equation, I get mu prime over mu equal p of x, but mu prime over mu is nothing but log of mu prime, there's no minus here, equal p of x. And then you deduce that mu is in the form a e to the antiderivative of p of x dx. Now, since I need one integrating factor, I choose a to be 1. So if I choose a to be 1, the integrating factor of my original function y prime plus p of x y equal to 0 is mu of x equal e integral p of x dx. I stress the fact that this is one of the integrating factor. You can multiply the ODE by 2 times e to the integral p of x dx, but while doing so, I just choose a to be equal to 1. So this is generally the method. So having a linear ODE for order 1, I multiply by the integrating factor, and I expect the left-hand side to become a total derivative. So let's do now a couple of examples. So the first ODE I want to discuss is the following. So example 1. Let's discuss the ODE xy prime minus 3y equal x to the 5, and I'm assuming that x is positive. So in general, in order to get the integrating factor, I want the factor that's multiplied by y prime to be 1. So first I divide here by x. Of course, I can do this because x is positive, and then I get y prime minus 3 over xy. I'm dividing everything by x, and then I get this is equal to x power 4. Now the integrating factor, as we said, now what is my p of x? This is my p of x. So the integrating factor mu of x is equal e to the integral of 3 over x minus 3 over x dx. Now this is the antiderivative of minus 3 over x, so this is e to the minus 3 log x, and this is e to the log x power minus 3, and this is equal x power minus 3, which is nothing but 1 over x cubed. So I multiply the equation, called here equation 2, by 1 over x cubed to get 1 over x cubed y prime minus 3 over x4 y is equal to x. But notice that this is nothing but 1 over x cubed y prime. So you always get the integrating factor times my original function, all prime, equal to x. And now I have a function, which is here 1 over x cubed y, whose derivative is x. Integrating, I get 1 over x cubed times y is equal, the antiderivative of x is x squared over 2 plus a constant, and this implies that y equal x5 over 2 plus c x cubed. And that's my solution to the original ODE. Maybe another example. Let's solve, in this case, an IVP. So example 2. So I want to solve the ODE, the IVP x plus 1 dy over dx plus xy equal to 1 with the initial condition y of e equal to 1. Now this is clearly a linear ODE, and I'm solving near x equal to e. This is x0 and this is y0. So this means that I can divide, so step 1, let's say this, is to solve the ODE, which is x times x plus 1 dy over dx plus xy equal 1, which is linear. Now, since I'm solving near x equal to e, then I can divide by the factor of y prime, which in this case is x times x plus 1. This is not 0 for x close to e. In fact, this is 0 only for x equals 0, x equal to minus 1. So this is e, this is 0, and this is minus 1, which kind of the bad points here. And now I'm solving near x equal e. So I get dy over dx, so I divide by x times x plus 1, and I get dy over dx plus 1 over x plus 1 times y equal 1 over x times x plus 1. And now I need to multiply this equation by an integrating factor. In this case, this is my p of x. So multiply by mu of x equal e to the integral 1 over x plus 1 dx. Now this is equal e to the log of absolute value of x plus 1. But notice, since I'm solving near x equal to e, this implies that absolute value of x, this implies that x plus 1 is positive. So this is equal e to the log of x plus 1. This is because we are close to x equal e. And this gives me x plus 1. So I multiply by x plus 1, and then I will get a new, and then I get dy over dx times x plus 1 plus y equal 1 over x. Now notice that the left-hand side is nothing but the derivative of x plus 1. This is your mu times y, all prime. You can check it using applying product rule. The derivative of x plus 1 times y is x plus 1 times the derivative of y plus the derivative of x plus 1, which is 1, times y. And this is equal 1 over x. Now this is, again, I apply the antiderivative method, so I integrate. And remember that x is close to e, so x is positive. So this gives me x plus 1 times y equal log of x plus a constant. We obtain that y of x is equal log of x over x plus 1 plus a constant over x plus 1. Now recall that this is not done because here I have IVP, so step 2, I have y of e equal to 1. So replacing x by e, we have 1 equal log of e over e plus 1 plus e over e plus c, sorry, plus c over e plus 1. So this gives me c plus 1 over e plus 1, and this implies that c equal to e. So the solution to the IVP is y of x equal log x plus 1 over x plus 1. Now let's discuss a little bit where is my solution defined. Now remember, I'm solving near x equal to e, so I need the denominator to be different than 0, so x should be different than minus 1, and x should be also positive because I have here the function log x. So the largest interval containing e for which I have a solution is, this is true for x belongs to 0 infinity. This is the interval where my solution is defined in a neighborhood of x equal to e. Thank you very much, and that will be it for linear equation. You can now finish all the exercises in the syllabus of chapter 2.3. Thank you.